Morning, everyone. Today we're going to go over Calc Review 12. This might be sort of a lengthy video because there were a lot of questions and really a lot of different questions. So I want to try to make sure to cover all of the questions. And really, to me, the best way to do that is to actually go through all four parts of of both problems. All right. So part A for each problem they're both actually pretty much the same thing, but we'll go through them. So part A for this teapot problem says to use the data in the table to approximate the rate at which the temperature of tea is changing at this particular point in time. So we have to pay attention to what we're given in the table. We're given the temperature of the tea at any given time. And we are, of course, given just 5 choices of time. So when we want to approximate the rate at which the temperature of the tea is changing, that's another way of saying what is h prime of t when t equals 3.5. Now, we're not given a derivative function, and we're also not given t equals 3.5, anything about t equals 3.5. So in order to approximate the slope of the tangent line when t equals 3.5, I'm going to choose 2 points, 2 known points on h around 3.5. And I'm going to use those 2 points to calculate the slope of the secant line. And that secant line slope will be an approximation for the slope of the tangent line. All right, so that's all I've done here. So I said that h prime of 3.5 is approximately equal to this slope here, which is, as you can see, this is just the slope of the secant line. And those units, of course, are degrees Celsius per minute, right? Because if h of t has units of degrees Celsius, that's the numerator up here. That's a change in degrees Celsius, whereas the denominator is a change in time. So my units end up being degrees Celsius per minute. Right, and that's important. Like, you will not get full credit if you don't include your degrees. I'm sorry, I meant to say not your degrees, but your units. Part B. Now things get a little bit more complicated from here. Using correct units, explain the meaning of something like this. So where we take an integral and we divide an integral of a function and we divide by the length of the interval, right? Notice we're integrating from 0 to 10 and then we're dividing by 10. That's not just an arbitrary choice of dividing. We're dividing by the difference between the upper bound and the lower bound of the limits of integration. In general, when we integrate a function and divide by the length of the interval, this gives us the average value of that function on that interval. This is something that's pretty important to remember. And you can think about it in terms of the units, I think. So when we integrate h of t times dt, we're really summing together a whole bunch of Celsius spelling error. We're really adding together a whole bunch of Celsius minutes, right? We're adding together infinitely many quote unquote Celsius minutes together, but we're also then dividing by, when we divide by 10, that is 10 minutes minus 0 minutes. So we're dividing by minutes. So when we evaluate this expression, we take our Celsius minutes, divide those by minutes, and we end up with just simply degrees Celsius. And so really what we're doing, think about it when you average like a set of 4 numbers, you add those 4 numbers together, and then you divide by the number of numbers. So this is sort of the analogous average operation with a continuous situation. All right, so when we integrate a function and divide by the length of the interval, we are getting the average, in this case, temperature of the T in degrees Celsius from T equals 0 minutes to T equals 10 minutes. All right, so that's what that expression represents. Now we have to go ahead and approximate that expression, and we're told that we want to use trapezoidal approximation. So there are 4 types of Riemann sums that you might and most likely will be expected to know come the day of the AP. And they are left endpoint, right endpoint, midpoint, and trapezoidal. Don't ignore trapezoidal just because you think it's the most difficult one. That might be the case, but it's also quite possible that they'll choose it. All right, they're not just going to ignore it, and so neither should you. So in general, just going up here, just showing you an example of a trapezoidal approximation. So take a look up here. You're given a function, and the way a trapezoidal approximation is built is you take the given points and you connect them like so. All right, so instead of building rectangles, you actually literally take the points on the function and connect them with a line segment. All right, and so when you do it that way, in this case, you form 2 trapezoids. All right, so these are the 2 trapezoids in this example. And so in this example, I would be calculating something called T sub 2. So it's a trapezoidal approximation with 2 sub intervals. And in general, the area of a trapezoid is 1/2 times the height times the sum of the 2 bases. This is a little tricky because the trapezoids that we use when we do a trapezoidal approximation, the trapezoids are kind of sideways. So the height is actually going to be our delta x, and the base lengths are going to be the heights, or not the heights, the base lengths are going to be these vertical lengths, which are defined by whatever your function is. So base 1 for this first trapezoid will be f of 0. Base 2 for this first trapezoid will be f of 4. All right, and so that's why for trapezoid 1, I have 1/2 times 4. So that's 1/2 times height times base 1 plus base 2. The second trapezoid, something similar. I have 1/2 times the height. The height is delta x, so to go from 4 to 10, that's a change of 6. And then the 2 bases are f of 10 plus f of 4. All right, and so that would be the trapezoidal approximation for this particular example. Going down now to the problem that we are actually interested in. So one thing that's important is don't forget this 1/10. Okay, that's not part of the Riemann sum, but it is part of the expression that we're trying to calculate. So notice I'm doing, again, T4, so there's going to be 4 terms. So that's why I have these 4 1/2s here, because I'm doing 1/2 times height times base 1 plus base 2. I'm doing that 4 different times for 4 different trapezoids. So that's why you see 4 halves. This 2, 3, 4, and 1, those are the respective heights. So going back up here, delta x, or in this context, delta t, is 2, 3, 4, and 1. So that's where those numbers are coming from. And 60 plus 66, that's base 1 plus base 2 of the first trapezoid. And how do I determine those? Well, those are the y values in this first interval, 60 and 66. And the same goes for the second interval, at the third interval, and the fourth interval. All right, so I'm not going to go into those details for each and every one, but that's the idea. And then using your calculator to evaluate, you end up getting 1059 over 20 degrees Celsius. Again, we do end up simply with degrees Celsius because the numerator is Celsius minutes, the denominator is minutes. Part C. Evaluate the integral from 0 to 10 of h prime of t dt, and then using correct units, explain the meaning of the expression in the context of this problem. All right, so this is a fundamental theorem of calculus part 1 problem. So if I want to integrate h prime of t dt, the fundamental theorem of calculus from 0 to 10, FTC part 1 tells me that I take the antiderivative of h prime evaluated at 10 and subtract from it the antiderivative of h prime and evaluated at 0. Well, the antiderivative of h prime is just h. We happen to have a table of values for h. So this is simply just going to be h of 10 minus h of 0. Looking those values up in the table, we get 43 minus 66, which ends up being negative 23 degrees Celsius. Now, what does that integral mean? Well, as I've mentioned many, many, many times at this point, when we integrate a rate, we get the net change in temp. Well, within this context, this is the rate of change of temperature that we're integrating. So when we integrate that rate, we get the net change in temp over that period of time. And so that's what I wrote in words here. I wrote the integral from 0 to 10 of h of t dt represents the net change in temp of the t from t equals 0 minutes to t equals 10 minutes. All right, so I'm including the units. I mean, really, to be totally correct, I should say net change in temp degrees Celsius of the t. So I should include that information. All right, going on to part D. We are now given some new information. We're told that there are some biscuits that are 100 degrees Celsius at some initial point in time. And we're told that the rate of change of temperature of the biscuits is this function b prime of t. And we're asked to determine how much cooler the biscuits are than the t at t equals 10. So the thing is, we know the temperature of the t at t equals 10, right? That's this number here, 43 degrees Celsius. We just need to somehow use the information given in part D to determine the temperature of the biscuits at t equals 10. And this is easily done. So again, we're given some initial temperature of the biscuits, and we can now use this formula that we've seen, hopefully at this point, many, many times. The temperature of the biscuits at some point in time is equal to the initial temp plus the rate of change, plus the integral of the rate of change of temperature from 0 to 10. Again, when I integrate a rate, I get net change, in this case, of biscuit temperature from t equals 0 to t equals 10. And so when I evaluate that integral, it tells me that the biscuit temperature dropped by 65.8172 degrees Celsius. And so when I add that to the initial temperature of the biscuits, I see that the biscuits are now 34.183 degrees Celsius. Again, h of 10 is 43 degrees Celsius. And so I can make the claim that the biscuits are 8.817 degrees Celsius cooler than the t at time t equals 10 minutes. All right, so there you have it. That's problem 1. Let's get right into problem 2. Very similar. We are given a table of values. The important thing to note here, though, that in this situation, we are given a table of values that represents a rate. All right, whereas up here in the first problem, we were given values that represent a temperature at a particular time, not a rate of change. But we're in part 2, we're given a rate of change. So that will come into play. All right, part A asks us to estimate r prime of 2. Well, r prime is just the derivative of r. And in order to estimate that, just like the previous problem, I need to approximate the slope of a tangent line. Well, in order to do that, I have limited information to actually do that. So I'm just going to use the information I have by choosing a point that is close, or 2 points that are close to t equals 2. And I'm going to use those points to get the slope of a secant line. That secant line is meant to approximate the slope of a tangent line. All right, so I chose the points at t equals 1 and t equals 3, and simply r prime of 2 is equal to negative 240 over 2. Make sure that you indicate the units of measure. Since r of t is liters per hour, and we're dividing by hours, then r prime of t is going to be liters per hour squared. Make sure to indicate that. All right, part 2. Left Riemann sum with 4 subintervals to estimate, indicated by the table, to estimate the total amount of water removed from the tank during the 8 hours. All right, total amount of water removed from the tank during the 8 hours. And the question is this an overestimate or an underestimate of the total amount of water removed? All right, so I think drawing a diagram here is going to help us determine the second part of the question. It's also going to help us understand why we can say that what we are about to integrate is a total amount of water removed rather than a net amount of water removed. So let's see what we know about R of t. We're told that R of t is differentiable and decreasing. So the fact that R of t is decreasing means as I move from left to right, or as x increases, then R is always decreasing. There's not going to be a situation where R goes up in between 0 and 8. So if I draw a diagram, I just chose the 5 points that we were given, and I connected them with a line or a curve that is decreasing. Right, we're told R of t is decreasing on this interval, so we know that it must be the case. Another thing I want you to notice is that R of t is always positive. It would be impossible for R of t to be negative because even if it were negative at any of the unknown points, in order for that to happen, it would have to go to negative and then jump back up to positive, but that's not allowed because we're told R of t is always increasing. So that can't happen. So R of t is always positive, and we also know that R of t is always decreasing. So when I draw my left Riemann sums, you can see right away that this Riemann sum is going to be an overestimate. Okay, so let's get into the calculation. Actually, in general, like I mentioned before, when I integrate a rate over a to b, this represents what we call the net change in f from a to b. Yet in this situation, I'm using the integral of the rate to represent not just the net amount, but also the total amount of water removed. Why are we allowed to do that? Well, remember in a previous video, I said that if we want the total change of a function over a time period, I would take my function and apply the absolute value. I will take my rate function and apply the absolute value to it. And that would give us the total change in f from a to b. However, like I mentioned before, since R of t is always positive, in this case, the function R of t is exactly equal to the function of absolute value of R of t. So in this situation, it is exactly the same to say net amount of water is equal to total amount of water removed over this interval. So anyway, moving on. So in order to get total amount of water, all I need to do is integrate the rate of change of water from 0 to 8 using a left Riemann sum. I have this expression. All right, I'm going to allow you to sort of take the time and pause the video to see where I got my numbers. I'm not going to go into the details. Moving on to part B. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. All right, so we basically want total amount of water in the tank at some point in time. The thing is, you have to understand that there's some tank, but there's water being pumped in, and there's also water being pumped out. So we need to take both of these things into account. So at this point, we haven't used our rate in function, but it is there. That's W of t. So rate in is W of t, whereas our rate out is R of t. All right, and at any particular time, there's some amount of water in the tank. I'm going to call that big T of t. This is not a rate, but it is the amount of water in tank at time all right, so that's basically what's going on. We're going to use the rate in and the rate out functions to determine the amount of water in the tank at time t. Of course, it is also important to know that at time 0, we start out with 50,000 liters of water in this tank. With that information, we can set up the following expression. So again, let T of t represent the total water in the tank at time t. T of 8 then will equal, T of 8 then will equal the total amount of water initially. Then I want to add to it the total amount of water that was pumped in. And I'm going to do that by integrating W of t dt, or I'm going to integrate the rate in from 0 to 8. And then from that, I'm going to subtract the rate out from 0 to 8. Remember, what does this tell me? This integral tells me net change in water pumped in, whereas the other integral represents net change in water pumped out. All right, going forward and using those and looking at the actual values we get this 50,000. That's of course the initial amount of water in the tank. This 7,836.195, that represents the total, the net, which is equivalent to total in this case, amount of water that was pumped into the tank from 0 to 8. And this 8,050, as we saw before, represents the total amount of water that was pumped out, or the total amount of water that was removed from the tank over this time period. So really overall, there wasn't really too much water. There's not really a huge change in the amount of water over this time period. As you can see, when t equals 8, there are about 4,900, wrong comma, low placement, 49,786.195 liters when t equals 8. And again, the reason I put my approximation here is because this 8,050 is an approximation from the prior problem. By the way, going back to part B, I forgot to mention why it's an overestimate. We would say that this Riemann sum is an overestimate because left-hand Riemann sums will always overestimate decreasing function areas. Okay. Part D. This one was tricky. There were a lot of questions about this, but over this time interval, The question is there a time when the rate at which the water is pumped into the tank is the same as the rate at which the water is removed from the tank? Explain why or why not. So something that's important here that I'm going to highlight is our function for W of t is just an exponential, and that is a continuous differentiable function over the entire interval. So W of t is continuous and differentiable. Similarly, we're told that R of t is differentiable, which implies that it's also continuous. All right, so we're dealing with two functions that are continuous and differentiable. Now, when we take W of 0, using your calculator, you'll get that that is equal to 2,000 liters per hour. And you can see from the table that that's greater than R of 0. So graphically, let's just say that this is W of 0 and this is R of 0. Graphically, W of 0 is above R of 0. Moving forward, when we use our calculator to calculate W of 10, we get 13.476 liters per hour. And we see from the table that that number is lower than R of 10. So graphically, let me change these axes so graphically, even though R is decreasing, it turns out that W of 10 decreases a lot faster as time goes on. And so when we connect R of 0 to R of 10, and then when we connect W of 0 to W of 10, since both are continuous and differentiable functions, it's clear that they must intersect at some point in order for these two statements to be true. And we know them to be true because we just checked that they are. Right, so we would argue the following. Since both functions are differentiable, and since W of 0 is greater than R of 0, and W of 10 is less than R of 10, there must be some point at which the two functions intersect. All right, as long as you have all of this information here, this argument would be perfectly fine. All right, ladies and gentlemen, this video has gone on for a long time, so I'm going to stop here. I hope all is well. If there are any follow-up questions, please either email me, post to the stream, anything, just let me know. All right, take care, folks. Bye.